This is lecture 6 for chapter 5 for Math 202 Calculus 3, and in this lecture I will show you how to perform line integrals of scalar functions. These are lines that could be in 3 space. Okay, and part of this will be a derivation, but it also, which I know when you're looking at trying to just get the homework done, you might not care so much about, but I hope you care a little bit about it. But also with the derivation, I'll show you how to do it and end up with an example. What we mean by a line integral is integrating the scalar, or in later lectures a vector function, but in this case just a scalar function. So integrating a scalar function along a path that has been parameterized. It has line in there, it doesn't mean it's a straight line. It could say path integrals would be better, but they're always called line integrals. Of course, you use them in physics. They appear frequently in physics and engineering, and but if you study in math complex variables, line integrals also appear there, where they're called contour integrals. Now, right here is the general form of a line integral for a scalar function. Remember, f is our scalar functions. Well, it's just scalar field, meaning a scalar function f. That means something that assigns a scalar value to everything in space. Temperature would be a scalar field, right? Every point in space has its own unique temperature, and that's a scalar value. Okay, and this is what the integral looks like. Of course, getting from here to there is what the purpose of this lecture is. The path has already been parameterized. We're just going to go from T1 to T2. This is not a surface. It's going to be a line in space, and it's parameterized. So this is a mapping from R1 into R3 to define the path. Okay, so this is the derivation, and during the derivation you'll learn how to do this, how to construct these integrals. So what we're talking about is a line or a path in space that has been parameterized, and here's our parameterization. Looks like this. We assume it's a continuous function and it has a non-zero continuous first derivative, which I'll write as our dot. We're assuming the path is simple. That means it doesn't fold back on itself, doesn't cross itself, and it is also oriented. To derive this integral, let's start by looking at the Riemann sum for a single variable. So here's a Riemann sum. Remember that from Calculus 1. This is a sum over some endpoints in x. F of x star means the value of x within the interval delta x, and then is multiplied by dx. Perhaps you don't recall what this is, so let me draw a little bit of it here. Okay. Say I'm trying to integrate this function. Okay, and here's the function, here's x, and this is a straight line, yeah. Okay, so, forgetting that for a moment, the Riemann sum is I take this integral and I divide it into little sections of width delta x. Okay, each one of these is the same width. You may not be able to see that, but they're the same width. Okay. And f of x star is the value of the function at some place in this little interval. It could be at this endpoint or that endpoint. It could be at the middle. It's complicated ways to figure this out. It doesn't matter. So you're taking the value of the function somewhere. So that would be f of x star. Multiply it by here, and you get the area. Let's just do something simple. Let's do an endpoints. I guess it's right endpoints, and that gives me my area here. Then I move over here, and I take this one, and I get a little rectangle here. Now if I add up all these rectangles, I get an approximation to the area under that curve. And it becomes a better and better approximation as this delta x approaches 0, and in which case this sum approaches the integral. Now let's move to taking the Riemann sum in multivariable calculus. That means over several variables. Okay, so we have the function, and we have, instead of just dx, we're going to have a little arc length. This is in 3 space, so we're still talking about a path, a line. All right, and we want to integrate along a particular line, so we're going to take the value of the function and we're going to multiply it by the length of a small length of a segment of the line, which I'm going to call ds. And we'll say in the limit, that will end up being the integral of f along that path. Now I put a footnote that you can't read into the slide. It's in the written lecture too, and it has to do with what is delta s. Okay, for me, delta s is just the difference in endpoints. So here's the path. R is the path that you're going to integrate along. You have parameterized it by r of t. Let me write that for you. So this is r of t, which is the parameterization of this particular path in space. In this case, just along this line here. Okay, now the difference between these endpoints I write as delta s, and it is a straight line. You can't really see it here, but it is a straight line. And okay, here is remember, this is a parameterization, so each vector starts at the origin and goes out to here, and the endpoints, when you pick up the endpoints, you get the line. Delta s is just the difference between those two values, and it is a straight line segment. Stewart and Thomas, they use delta s as the arc length along here. I don't think you need to make that assumption. Actually, turns out things are a little bit different if you do, but you'll end up with the same thing. But I like to just assume that's a straight line segment between there. So in that case, my correspondence between delta s and delta x in the Riemann sum is the same. So by definition, of course, the length of that segment, delta s, is just the absolute value of the difference between r at the upper endpoint minus r at the little endpoint. Okay, what is in the limit the derivative of r? R dot in the limit is the difference between r at the two endpoints divided by delta t. Okay, just the difference quotient. So I'm going to rearrange this and write delta s as the absolute value of r dot times delta t. Now I have this line segment in terms of the parameterization t. Okay, so instead of just delta s here, I can write the magnitude of r dot, magnitude of the time derivative of the parameterization times delta t. I'm still in the Riemann sum, and we have to move out of that. Okay, so the next thing I do is evaluate the function along the path. I don't care about the function any place in space except along the path. So I'm going to parameterize it by using composition. F composed with r. This looks messy, but it means F composed with r. And when you see an example, it's obvious. You don't have to worry about this notation. So in other words, I'm going to compose F with r, and that will give me the value of the function along the path. So as t changes, I'm going to find the value of the function right along that path. So I'll substitute that. So now I have, don't worry about this one, F composed with r, that's sticking the function right on the path, times the absolute value, the magnitude of the it's the magnitude of the time derivative of the parameterization times dt, and then integrate between two time endpoints. So here's an example. I'm going to have the density, that didn't come out right. Here's the density of piece of wire, and it's the density per unit length. I think I went over that in calculus too. So let's say it's y plus 3z. So as y and z are changing, the density of this material is changing. It's big ingot, just big hunk of this material. Okay, now you've got a path along a wire. I'm going to pull a wire out of this, and I want to know how much mass is on it. So let's say we have this particular wire here, which would be a helical, just a helical wire. I want to know the density along the wire. So first, I take the function, which I'm calling rho instead of f, and I compose it with the parameterization. That becomes sine t plus 3t, right? Because, let me clear the screen a second. I think sometimes people aren't sure how to do this. Okay, it's like this. Every place you have an x, you have to put cosine t. Well, there's no x's, so forget that. Every place you have a y, there's only one y here, you put sine t. That's why the sine t is right here. Every place you have a z, you put t. Okay, So you just compose them together. And when you've composed them, you get sine t plus 3t. That is the function composed with the path. Now I have the density along that wire, which is changing in time. Okay, so it's in terms of the parameterization now. Take the first derivative, you're going to need that, and its magnitude, in this case turned out to be just square root of 2. Now I can find the mass along, say I'm doing 3 turns of the wire, that's why I'm going from 0 to 6 pi, 3 turns of this wire. So F composed with R, we already did that right here, and that's what appears here. Okay, then we have the magnitude of the time derivative of the parameterization, which is square root of 2, and we see that here, and now we just integrate. So that's how to take the line integral of a scalar field. You need to parameterize a scalar field, that's what we're calling R. You need to compose the function, the scalar function, with the parameterization, so then you do have the function in terms of t, the parameter. Take the time derivative of the parameterization, again you assume this is a continuous function, and take its magnitude, and there you go. Now you integrate with respect to time.